All right, if you're getting ready for your GCSE physics exam, then you are in the perfect spot. Today, we're diving deep into a really important topic, the motor effect. That's AQA section 4.7.2, by the way. So let's jump right in. Ever wondered what actually makes an electric motor spin, or how a loudspeaker pumps out sound? It might feel a bit like magic, but it's all down to one fundamental principle in physics. And by the end of this, you're going to know exactly what it is. Okay, here's the game plan. First, we'll cover the absolute basics of electromagnetism. Then, we'll get to the main event, the motor effect. After that, we'll look at a super handy tool called Fleming's left-hand rule, see how it all works in motors and loudspeakers, and finally, we'll wrap up with the key formula you'll need. Simple as that. All right, first things first. Before we can get to the motor effect, we have to talk about the two things that make it happen, electricity and magnetism. It's all about how these two forces are connected. So here's the absolute core idea. You've got to get this down. Anytime you have an electric current, just electricity flowing through a wire, it creates its own magnetic field all around it. See that? It's like these invisible circles of force wrapping around the wire. Okay, but this is where it gets really clever. What if we take that straight wire and coil it up, kind of like a spring? Well, that shape is called a solenoid. And by doing that, we basically squish all those magnetic field lines together on the inside, making the field way stronger and much more uniform. And check this out. The magnetic field that our solenoid creates looks exactly like the field from a good old-fashioned bar magnet. You've got a clear north pole at one end and a south pole at the other. And that right there is the secret to how an electromagnet works. It's just a magnet you can turn on and off with electricity. So now we're ready for the main event. We know that a wire with a current has its own magnetic fields. So what do you think happens when we take that wire and stick it inside another, separate magnetic fields? Yeah, that's the big question, isn't it? You've got one magnetic field from, say, a permanent magnet, and then you bring in the magnetic field from our current-carrying wire. What happens when these two fields meet? Well, you can bet they're not just going to ignore each other. They interact. And that very interaction, that's what we call the motor effect. It's as simple as this. The two magnetic fields literally push or pull on each other. And that push or pull is a force. This force is what causes movement. It turns electrical energy into kinetic energy. That's why it has motor in the name. It makes things move. Okay, great. So we know there's a force. But which way does it go? Up, down, sideways? How can we predict it? Well, luckily, there's a fantastic little trick for this, a tool you'll definitely need for your exam. Just a quick heads up here, everyone. This next bit, Fleming's left-hand rule, is specifically for you higher tier students. Now, if you're doing the foundation tier, you don't have to memorize this part, but honestly, it's still super useful to see how it works, so stick around. Okay, get your left hand ready. For real, hold it up. Your first finger represents the magnetic field. Just remember F for first and F for field. Now, your second finger points in the direction of the current. And finally, your thumb shows you the direction of the motion, which is the force. Field, current, motion. This little hand rule is your best friend for any motor effect question, I promise. So now that we can predict the force, let's put it to work. Let's look at the most famous application of the motor effect, the electric motor. This is the secret behind, well, pretty much everything that spins using electricity. And yep, you guessed it, another quick heads up. Understanding the nitty-gritty of how an electric motor works is a higher tier topic. So how do you get something to spin non-stop? Well, you take a coil of wire and pop it in a magnetic field. The current goes one way on one side of the coil and the opposite way on the other. Now, if you use your new left-hand rule skills, you'll figure out that one side gets pushed up while the other side gets pushed down, and that gives you your spin. But the truly genius bit is this thing called a split-ring commutator. Its job is to flip the direction of the current every half turn, which keeps the force pushing the coil around and around in the same direction. So clever. But the motor effect isn't just about spinning things. With a few clever changes, the exact same principle can create vibrations. And those vibrations, well, that's what makes sound. It's how you hear your favorite songs. Okay, and for your revision notes, let's be super clear on this one. The details of how a loudspeaker works are for higher tier students, and specifically for those of you doing the physics-only paper. So how does the speaker do its thing? The big secret here is that instead of a steady one-way current, it uses an alternating current, AC, which wiggles back and forth, matching the music's signal. This AC goes through a coil that's glued to a paper cone. Because the current is always changing direction, the motor effect creates a force that pushes and pulls the coil back and forth, super fast. The cone moves with it, and that vibration pushes the air, creating the sound waves that travel to your ears. Awesome, right? Okay, we've covered the what and the why of the motor effect. We've seen it in action. Now for the last piece of the puzzle, the math. How can we actually calculate how big that force is? And yep, one last time, I promise. This formula is another one for the higher tier students. You'll need to know it and be able to use it in your exam. So the magic formula you need is F equals B times I times L, or just F equals Bill. So what does it all mean? Well, F is the force measured in newtons. B is something called magnetic flux density. That's just a fancy way of saying how strong the magnetic field is. We measure that in Tesla. I is the current in amps, and L is the length of the wire that's actually in the magnetic field, and that has to be in meters. It's actually really logical. If you want a bigger force, you just need a stronger magnet, more current, or a longer piece of wire in the field. That's it.
Okay, let's wrap this all up with a nice summary. It's like a chain reaction, really. You start with an electric current in a wire, which causes it to have its own magnetic field. Then, you put that wire inside an external magnetic field, and the effect is a force, or motion. We use Fleming's left-hand rule to figure out the direction of that force, and we see it in action in things like electric motors. And finally, if we want to know the size of that force, we just use our formula, F equals BIL. See how it all connects?
And there you have it. That's the motor effect in a nutshell. We've seen that if you take electricity and a magnetic field, you can create motion. Which leads to a really interesting question, doesn't it? What would happen if we flipped it? What if we started with motion inside a magnetic field? Do you think we could create electricity? Well, that's a story for another time. For now, best of luck with your revision.